Hello everyone and welcome. My name is Karim. I'm with IPACK Solutions, Cadence channel partner in the MENA region. So in this tutorial, I'll introduce Cadence Celsius EC by demonstrating its basic workflow. We'll build a simple electronic system, set up a thermal simulation, generate the computational grid, finally solve the model and review the simulation results. So let's get started. This is the Celsius EC graphical user interface. At the top we have a ribbon which organizes the available tools according to each stage of the workflow. We also on the left here have the model tree, which shows the hierarchy of all the objects in the project. We have on the right the property sheet based on which object is selected inside of our model. So for example, if I select the top side of the chassis, we can see its properties right here and change them, and it's also selected here in the model tree. Same thing, if I select something in the model tree itself, it will be highlighted in the GUI in the middle right here. We also have the object panel, which gives us all of the available objects that we can add into our model. To start off this project, we're gonna add a PCB into our chassis. When the PCB is added, there's the property sheet of the PCB that's automatically opened if we want to change anything before placing it. So right now I'm gonna leave it as it is. The PCB mainly is now placed in the chassis, which represents the enclosure in which all of the simulation will happen. So one thing we're gonna do is we're gonna adjust the placement of the PCB. This can either be done on the left here in the placement tab. So I want its X location, for example, to be 0, or we can even change its location using these blue manipulators right here. The green manipulators will allow us to change the size of some of the components. For example, if I select the chassis right here, I can resize it so that it comes right on the edge of the PCB. So it snaps on the edge right here. I can also resize it from here so that there's a little bit of space in the front and the back. So this will be mainly our inlet where the flow will come in, and the other side would be the outlet, and the sides there would not be any airflow going through the side. One thing I'm gonna do next is I'm gonna resize the PCB, make it a little bit larger, move the PCB up to around the middle right here so that the air can flow above and below it. The thing we're gonna do is we're gonna add a component. So we go to the object panel, we can drag a component and add it onto the PCB. The property sheet of the component is also opened. Let's press on OK. Let's just make it a little bit larger. So like this, place it roughly in the middle. We can use the top view so that we can see it a little bit better. Now for the component itself, the important thing is taking a look at the power and the thermal limits. So the thermal limit for this component would be 95 degrees Celsius. This is the maximum temperature for this component that is allowed. So if it exceeds this temperature, then it would have maybe this would be the operating limit. It would have maybe power issues, or it could simply fail. For the power itself of the component, I can either have the total power specified as 15 watts of a thermal design power, or it could have a power map that's distributed onto the component itself. It all depends on what we're simulating and how much detail we want. So in this example, I'm just gonna have this. The next thing we're gonna do is we need to cool down this enclosure. So I'll add a fan onto one side of the chassis. For example, here I'm gonna add onto the front side. I can go to the chassis side and add the fan from here. So just click on the fan. The fan will open the property sheet. I'm gonna place the fan also roughly in the middle. Let's use this. Let's take the front view. Make sure. In order to change the views, there are some shortcuts. For example, if I want the front view, I can just press on F on my keyboard, and similar to other views. Now that the fan is roughly in the middle, we can take a look at the cooling properties of this fan. So I'm just gonna make sure first that the placement of this fan is on the outside of the chassis rather than on the inside. The flow direction is in, as indicated with this arrow. The flow pattern will be uniform, and we're gonna have a fixed flow rate of 0.001 meters cubed per second. The rated speed will be 800 and the fixed speed will be 800. Celsius also supports fan performance curves and temperature dependent fan control if we are looking to do more realistic simulations. So since air needs both an inlet and an outlet, we would need to take a look at the other side, which would be the rear side of the chassis, and we would need to add an opening. So this would be a vent opening. We can either have it as a perforated opening, a slotted opening, a mesh opening. For my case, I'm just gonna have it as an open hole with the default environment as the outside environment. So highlighted here in red, we can see that we now have an opening. If we didn't add that, then the PCB would be closed from the side, which is not what we need. We need air to flow from the inlet to the outlet. Now with the model complete, we're ready to generate the computational grid. So first I'm gonna save the model. I'm gonna name it as tutorial, save. And I'm gonna go to the solver. Now in the solver bin, we have the option to first generate the grid. So Celsius automatically generates the grid based on the components and on the settings that are already placed inside the PCB. So we can look at the current grid. We can see that it automatically does some local refinement around the PCB itself. It does the same around the component and the fan to make sure that it captures all of these objects correctly. Let's hide the grid, and in order to solve it, all I need to do is just click on solve on my PC, specify the number of cores that I'm using, and click on start. Now we're just gonna wait for it to start so that we can take a look at what we're looking at when the simulation is running, and we're gonna skip to the end of the simulation. So first thing we look at is the component temperature. We want to make sure that the temperature of the component reaches a mean value. And another thing that's important would be the CFD solution residuals. We want all of the residuals to reach the bottom, which is 1. So once all of them reach the bottom, that means that the solution has converged. Now the simulation does not take a lot of time. It's almost done while I was talking. So let's just wait for it to end. I think it'll take around 40 seconds. Okay, so 39 seconds. We can see that the component temperature reached almost a mean value. Let's click on close. Now to visualize our results, one of the best ways is just go to the results tab right here, click on PCB plot, cooling system, surface temperature. We can see here that the maximum surface temperature that was reached was around 111 degrees Celsius, which is much more than the component can handle. So the maximum temperature allowed for the component is 95 degrees Celsius. We can also take a look at the streamlines in our system to see how the air is flowing in and out. So I selected the fan and the vent, and take a look at the streamlines inside of it to see how the air is flowing. We can see that the air is able to extract some of the heat from the component itself, but apparently not enough. Once you reach this stage, if you're modeling a real model, for example, there are two things you need to think about. One of them is, how do I need to cool down this component better? In order to do so, two things that come to mind, for example, would be getting a better fan. Maybe the fan should be stronger, or maybe simply for this component, maybe I can add a heatsink onto it. So in order to explore design changes inside of Celsius, it is made very easy in the version tree right here. So in the bottom left here, we can see the version tree. Right now, this is the baseline case, which is our case right here. What we can do is we can right click and create a new version. So I'm going to label this version as heatsink and click on OK. And I want to copy the full results of the older simulation. So I'm just going to click yes. Now we have a new version that's called heatsink, different than the baseline version. So if I click on the heatsink, what I can do is I can explore a new design change within this version, which is, for example, adding a heatsink. So I'm going to add a heatsink. Okay, the heatsink is now added onto the component itself. Of course, we can change some of its settings. We can make it larger, smaller, change the number of fins. For example, if I want less fins, I can put 10, for example. And finally, once that's done, all I need to do again is just solve. So it's the same exact thing as before, but I only added a heatsink. So I click on solve on my PC, and I have the option, instead of restarting the simulation from scratch, I can continue it from where it reached. So I'm going to click on continue, and once that's done, we're going to take a look at the results. So now that the updated simulation is converged, we can take a look at some of the results. So first things first, we can take a look at the airflow. We can see that air is able to extract the heat much better with the heatsink right now. And we can take a look as well as the surface temperature. So we can see that the maximum surface temperature reached in this case is 64 degrees Celsius. So the heatsink was a very good decision in this case, and maybe even overkill. So maybe even we can take a look at putting a smaller heatsink or changing some of the geometry of the heatsink so that we don't over engineer it in this case. But in this case it's fine. We explored this design change. If we needed to do another design change, then we would be able to do so as well. Mainly that's it. This simple example highlights the complete Celsius EC workflow from building a model all the way to evaluating the results. For larger industrial projects, Celsius also supports direct ECAD imports. So we can go to the import ribbon and we can take a look at importing mechanical CAD, electronic CAD, or even importing some specific properties from, let's say, a CSV file or things like that. So this would make analyzing complete PCB designs possible with minimal preparation. So that mainly concludes this demonstration of Cadence Celsius EC. Thank you for watching, and I hope this tutorial has given you a clear overview of the basic Celsius EC workflow.